Okay, we're going to continue with waves again, but today we're going to look at just sound waves and how that works with sound and air and things like that. First thing to remember sound waves are longitudinal, so that's our compressions. We get like a compression passing through the air, so we get these repetitions of compressions and so on. So that's how you're hearing me now. My vocal cords are compressing air, that transfers, and your ears hear it and interpret it as different sounds and different frequencies and so on. But normally sound travels through air, but it can also travel through water or solids or whatever, but the more dense it is, the actually faster it goes. So sound in water will be faster than sound in air, and sound through a solid like iron or something would even be faster yet. But we also have, just within air itself, temperature, humidity, pollution levels, all of those kind of things also affects the speed of sound. So at normal 20 degrees in dry air, which would be like our normal room temperature, our speed of sound is roughly 343 meters per second. As we get it colder and less humidity, it would get slower. So if we added humidity to a room, got it really moist, it would speed up a bit. If we get rid of the humidity, it slows down, and same thing with temperature. So you don't have to do the calculations, but you just have to understand that the speed of sound will change slightly. So usually in a question for this course, you'll be given that amount. So you'll be told that the speed of sound is 343 or 340 or whatever number. So today what we're going to look at is musical instruments and how they create sound. So a stringed instrument like a guitar, basically the string vibrates and it's amplified either through an amplifier if it's electric guitar, or just through the body of the guitar. The wooden hollow hole will echo and make the noise that way. And how we change the frequency or the pitch of the guitar is the smaller the string and the tighter it is, that makes a higher frequency. The bigger the string or the looser that we tighten it, it drops the frequency. So we can just basically change that in terms of the string itself. And then if we want to change it once it's set, we don't change the tension or anything. We just basically make the string longer or shorter to change the note by pressing down on the fretboard. Drums basically work the same thing. Each drum makes one sound, but we can change the size of it and the tightness of the skin, and that will change the frequency of the drum. So we're not going to worry too much about those. We're going to look at air instruments only for this course. We're basically going to look at two different types: an open, what we classify as an open pipe, or a closed pipe. So something that's closed would be like a flute. You blow in sort of the side of it, the air hits the closed end, and then it reflects and comes back out the open end. Or that'd be like blowing into like a bottle to making the noise. And most instruments are open, which would be like a trumpet, where you got to buzz your lips in one end and the noise comes out the other. So we'll start with open pipes first. So a trumpet, trombone, saxophone, anything like that, we either need to buzz your lips, or in terms of a saxophone, you blow on the reed and the reed vibrates, and that's what creates the waves. And then we can change that by blowing differently or faster, and that'll hit sort of different octaves. But basically, most instruments, they're designed to change the length of the pipe. So if we press on a valve of a trumpet, we're changing the different paths for the air to go through. We're changing the length of the thing overall, which would then produce a different note. So each sort of combination of the buttons, or like I think of a trombone, you slide the thing in and out, which you're physically just changing the length of the tube that the air is going through. So that'll change the different frequency. And then we just use our pitch changer in terms of our mouthpiece, and that'll hit the next octave. So most instruments would have about eight different notes that you could play, and then you buzz tighter, and that'll play another new 8, and so on. So you kind of hit different octaves or different levels. So for open pipes, we must have a antinode at one end and a node at the other. I got this mixed up here. So for it's an open pipe, they should be both open. Sorry, there's a bit of a typo. So we should have an antinode at the open end and another antinode at the opposite open end. So both antinodes at either end. So if we were to draw it in just a simple diagram, we would remember we're kind of creating resonance here. So we'd have our half of a wave would go down and it would reflect back as well. So if we get that to happen inside the length of the pipe, we will actually hear our proper note. So it could be a C or a B or whatever, depending on the length of the pipe. So if we actually look at this in terms of a wave, if we were to continue the wave, you'd see we would get basically what's drawn there is half a length. I didn't try to quite draw it as exactly the same distance, but you could see that would be one complete wavelength there and back. So our terms of a pipe, if we actually were to create sound, we just have to get half a wavelength to fit inside that pipe from end to end, and we'll create the right note. So we actually have two formulas. The length of the pipe then is half of the wavelength, and then we could use the velocity equals frequency times wavelength formula, solve it for wavelength, which would be V over F. And if we substitute that in, we end up getting 1/2 V over F, and we can rearrange that for F, and we end up getting V over 2L. So either of those two formulas are used to help us solve pipes. So we call that the first harmonic. That's the smallest amount, so we have to have at least a half a wavelength, and that'll create sound in an open pipe. So now, if we wanted a higher note, we just basically blow harder, faster, whatever. We can actually get that next octave, or what we call that is our second harmonic. So you can see in this case, our first harmonic was from there to there, but if we do another half of a wavelength, we get back to being an antinote again. So in this case, we actually have one full wavelength, but we're gonna change it a little bit. So when we do the second harmonic, we're going to use our same formula before. Remember, we had one wavelength over 2, or our frequency formula was V over 2L. So the only thing that's different now, if we're dealing with our next harmonic, our second octave, we're basically going to, because it's the second harmonic, we just put a 2 on there. So our 2's cancel. We end up just getting one whole wavelength, but it's easier to kind of keep it as fractions over 2. So you remember that every open pipe will always have a base of 2. So if we draw a 3, so there's one wavelength. If we draw the next open one, so it looks something like that. So you can actually see in terms of the diagram, we have 1.5 waves, or 3 halves, right? So one complete wavelength. Let me kind of show you in terms of the diagram here. So this is half a wavelength. So that would be 2 halves, and then there we'd have 3 halves. So we got 3 halves of a wavelength, and because it's an open pipe, all we're basically doing again is changing our tops. Remember, our first one was 1/2 wavelength, and our second harmonic was 2 over 2. So now you can see our third is 3 over 2. And it was the same thing for our frequency. We had V over 2L for our first, 2V over 2L for our second, and now 3V over 2L for the third. We can follow that pattern to fourth harmonic, fifth harmonic, and so on, as many as we want. But generally, most instruments, most musicians, you usually only hit the third. It's pretty tough to get to the fourth and fifth physically, just by being able to blow differently. So a closed pipe works almost the same, except we adjust the length again, but we have to have the antinode at the open end and a node. So I've got these two slides sort of mixed up. So we'd have a node at the closed end this time. So my open and closed pipes, these last lines were kind of backwards. So antinode at the open end, node at the closed end. So when we draw that, you can see in this case, so we have an antinode where we blow in, it's going to hit the closed end of the pipe as a node and then reflect back. So if we actually were to look at the amount of wave this is, that's actually, you can see, is a quarter of a wavelength. So from there is a quarter, and then we'd have a half, and then our downward part would be the other half. So we end up getting only a quarter of a wavelength instead of a half like we had for open pipes. So using the same logic, we'd have a quarter of a wavelength, and we can rearrange that formula to be V over 4L. So now, to get a node, so you can see here, there's our quarter of a wavelength. If we go 2 quarters or half, we'd have a node at both ends, so that's not going to work. We actually have to jump to get to 3 quarters. So you can get this sort of fish-looking kind of wave. So if we get to 3 quarters, that's our next octave. So we don't have a second harmonic for closed pipes. We just have first, third, fifth, and so on, but the formulas work the same. So our first one was 1/4 wavelength, or 1V over 4L. So now our third harmonic becomes 3/4 wavelengths, or 3V over 4L. And the fifth would be the same. So let me kind of sketch out a fifth. So we'd have our node here, and so there would be our 3/4, and there's our 5/4. You can see we've got, those are in halves. Right, so this is a half, this is a half, so that's one whole, and then we get a quarter at the end, which, so if we add those up, we could kind of chunk this into quarters if you want to see a little bit better. So there's 1/4 to there, That would be 2 quarters, 3 quarters, 4 quarters, 5 quarters. And I don't have them drawn evenly, but you get the idea. So fifth harmonic is 5 quarters. So again, we went 1 quarter wavelength, then 3 quarters for our third harmonic, 5 quarters for our fifth, and the same thing for the other formula. So here's everything in sort of our chart. So for open pipe, we have first harmonic as a half, second would be 2 halves, 3 halves, 4 halves, 5 halves, and so on. For close, we skip every even number, so we have 1 quarter, 3 quarters, 5 quarters. And to use those formulas work pretty simple. So let's look at this one. So we have an open-ended pipe that's 3.6 meters long. The first question is find the wavelength of the fundamental column. So we have an open-ended pipe, and we want the fundamental. So for open, we use F over V over 2L. So it's asking for wavelength. Oops, we don't want that formula, we want the other one. It's asking for wavelength, so that would be L equals a half wavelength. So we could simplify that to make it 2L equals wavelength. So all we'd have to do is go 2 times 3.6. So that means our wavelength for that note would be 7.2 meters. So that's pretty easy. Let's look at question B. It says determine the frequency of this note if the speed of sound is 346. So we can use the old formula. We could use velocity equals frequency times wavelength that we just calculated, but let's try it with the new formula. Actually, let's do it both ways. Okay, so we're looking for frequency. So that would be V over wavelength. So if our velocity is 346, wavelength we just calculated was 7.2. So we can calculate that. So let's do that quick. So we have 346 divided by 7.2, which is 48 hertz. Okay, but let's use the new formula. So we want frequency, so it's BV over 2L. So you can see we actually get the same thing. 346 over 2L is 2 times 3.6, which is our 7.2. So we do get the exact same answer. So it doesn't really matter whether you do it in 2 steps or just use the new formula. It works the same either way. Okay, so the next question here, it says, what would be the note played at the third harmonic? So now we want to jump to the third. So we want frequency again, but we're going to use third harmonics. That's 3V over 2L. So we basically just got to times everything that we just calculated by 3. So we could redo the whole calculation again. Or we could just take our answer, 48 times 3, and that gives us 144 hertz. So that would be the third octave. And the last question, it says, if we made the column longer, what would happen to the fundamental note? So if you made the length of the pipe longer, would that make the frequency higher or lower? So if we just look at one of these formulas, so we can see if we make the length longer, that would make the frequency lower. So the longer the tube, the lower the note. So an organ that has all these different length pipes, the longest ones would be the bass notes, the shortest ones would be the high notes. Or if you think of like a trumpet compared to a tuba, the tuba has a way longer pipe, so that gives us the low bass sound. So here's a couple other questions we can do quickly. So here we got a closed pipe, so we want fundamental. So for closed, remember our formula is quarters. So we'd use, let's go back to this one again. So closed pipe, we want V over 4L instead of 2L. So that's really the only thing you got to be careful of. If it's open, use 2. If it's closed, you use 4. So V over 4L. So we put in our 343 divided by 4 times 20 centimeters. Make sure you change that to meters. So 343 divided by 0.8 gives us a frequency of roughly 429 hertz. So now if we do the same thing, but we want the third harmonic, it'd be just 3V over 4L. Or we can just go 3 times our answer, because that's all that we're really changing. And that gives us 1286 hertz. And the last one, the fifth harmonic, basically the same thing again. We can just put it into our formula, 5V over 4L. Or we could take our original and times it by 5. So 429 times 5 would be the same thing. And we get 2145. So that means for a 20 centimeter pipe, those are our 3 harmonics. Our basic one would be 429. We blow faster, different, we get to the next higher one, which is 1200. Do it again, we get to 2145, and to get to the 7th would be that much higher yet, which is pretty difficult. So like I said, most musicians can hit the 3. You can sort of hit your 3 basic